turning points. Okay, so if you want a Venn diagram for it, okay, I can get rid of this now. It's not going to be one of those overlapping ones. You've got stationary points, which is like a family of different kinds of points where the derivative is equal to 0. Okay, but within that, there's a subset, right, of turning points. Okay. And it's smaller. There are some stationary points, as you'll see in a second, which are not turning points. What is a turning point? What does the name suggest? It turns. Okay, so here I was increasing, and then the apple turned around, right, and it became decreasing. Okay, so therefore this is not just a stationary point, but also a turning point. Now, there's my sort of plain English definition. I said that a stationary point was dy on dx is equal to 0. What kind of technical dy on dx definition could you give to me that defines a turning point? What does it mean to be a turning point? Okay, so that's what it's doing. How would we describe that in terms of...
Negative to positive.
Okay, so here's my definition, which is sort of that, but a little bit different. Okay, a turning point exists where dy on dx, this is why I started off with signs, right? Where dy on dx changes sign before and after. Okay, so in this example, my apple, right? If I were to draw on there, what is the sign of the derivative? Okay, well, because this part here, they're all increasing, right? So it'd be positive, 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 okay? And then there's this point, and then after that, the derivative, the gradient function, is negative, right? So because dy on dx has changed sign, that's what makes that a stationary point, okay? Now, turning points are trickier than stationary points. That's what I'm sort of implying here, okay? So first.